Hello everyone and welcome to another video where this is really a follow-up to the latest video I did on the relativity of simultaneity, where fittingly Space Audits have done a follow-up, so I can react to their follow-up to the original video, which serves as my follow-up for my original video, so you know we are really fits like hand in glove. So let's listen what they have to say about relativity of simultaneity, which again apparently is false, even though last time it was more a problem of their understanding. And I have an inkling that this is what will happen today.
All right, lads, this is a follow-up to the relativity of simultaneity principle. So the standard example that's given is that suppose you have an observer C and an observer D on a moving train. The C observer is stationary. The moving train intersects with the stationary midpoint of the observer C. And at the exact moment that happens, there's a simultaneous lightning strikes at points A and B that are not attached to the train. And from the moving observer's point of view, because he's moving towards B, he's going to perceive that the lightning strike B occurred first, and the delay from the lightning strike from A to catch up to the midpoint of the moving observer will be different from the physical location of the observer C at his midpoint. Right. So they're saying that because of the perceived difference in the simultaneous event, that therefore in physical reality, these two lightning strikes did not occur simultaneously. Okay?
This is not exactly what we're saying. You're getting somewhat close here. The clue about relativity of simultaneity is that every reference frame has a different definition of what they would call simultaneous. And this is why in relativity, when we talk about simultaneity, we talk about it in the simplest kind of way to do it, such that one event could not influence the other event. This is what we truly mean by simultaneous in cases like this. Explained this in my last video. If you haven't seen it, I would encourage you to watch it before this one, because I kind of, I kind of expected you know by now.
Even though the stationary observer registers them as simultaneous due to the principle of relativity of simultaneity, these two coordinate systems regarding time are not connected to one another. This coordinate,
I mean, they are connected to one another via a transformation of some sort, if you know that d is moving at a constant velocity.
time defined for the stationary observer is called coordinate time, and they say that this time is arbitrary. And the moving train observer has
No, all time is more or less arbitrary because it can change with reference frames. So
what's called proper time. His time will be different as a function of the square of his velocity over c squared. So what they're saying is that time is not connected between these two, right? And the perceived...
I mean, it is, just in a very specific way. Because time, you do a Lorentz transformation and then you get the way that moved observers relative to stationary observers experience time and things like that.
event will occur in a different order than for the stationary observer. Now, this is an apparent effect. In reality, lightning striked, stroked or striked, who knows? Lightning striked both of these A and B points at the same time.
You say reality here, but there is no... Again, the reality of the stationary observer is just as valid as the reality of the moving observer, both of which experience different events in a different order, the same events in a different order, rather. So when you say in reality, that shows me that you kind of don't understand one of the main points of relativity, and that is that every observer has its own correct reality, right? Because otherwise you would postulate that there is one absolute reference frame, in this case the one from the stationary observer, which is not what relativity says. This is very much not what we say. And it is what you say, but it's still defining one reference frame as absolute is arbitrary.
For the stationary observer, and that's the event that occurred in reality, right? Now, the perceived motion of the train, or I'm sorry, the observer on the train who's moving perceives the events occurring differently, but that doesn't change the fact that the event actually happened in reality simultaneously. Now, here we have...
Again, you can't say in reality. That is not how that works.
Have Einstein breaking down clarification on this, because some people will say, well, no, it's just the apparent effect, but the event actually occurred simultaneously. No, that's not what Big Ein says. So here we're going to read off what Einstein says, and then we're going to get into a variant of the train explanation that's a little more simple to follow, and it doesn't leave any wiggle room for the midpoint argument, for the time that it would take for the information to go to the moving platform, or I mean to the moving observer. They're saying that due to that delay, you would be physically in a different position, therefore the event wasn't simultaneous. But oh, and how could we ever know? Okay, well, let's read from Einstein, and then we'll get to the new example. Are two events like two strokes of lightning, A and B, which are simultaneous with reference to the railway embankment, also simultaneous relatively to the train? We shall show directly that the answer must be in the negative. When we say that lightning strikes A and B are simultaneous with respect to the embankment, we mean that the rays of light emitted at the places A and B.
It is, I believe, what he's explaining here is essentially what I explained in my last video about the two lightning strikes and the train and who registers which event at what time and things like that with moving observers and things. I think I explained that pretty nicely. Down here, particularly, every reference body, coordinate system, has its own particular time unless we're told the reference body to which the statement of time refers. There is no meaning to the statement of an event, of the time of an event. That is precisely what I explained, or in other words, obviously, but this is what I explained, so I will just skip this section
where
in the
lightning
interest
strikes
of time.
occur. In the event, lightning strikes in the bond. Okay.
Okay.
So the example given here with the lightning strikes in the bomb reaching the midpoint, sure. There's an apparent effect which you would not perceive the event as being simultaneous. But did the event occur in?
If it's an apparent effect, then how come that you actually register the two events as not happening at the same time if it's apparent? What does apparent mean in this context to you? Because the way you say it is as if it's not an event in reality, but yet the signals are registered at a different time in reality. So it's not apparent, is it? I know why he says apparent, because he doesn't believe in it, but I don't care. So yeah.
In reality, simultaneously for both observers, regardless of the apparent effect. Now, when you get into the
Again, in reality is not a defined term, and what you call in reality is not the reality for someone else. So he I love how he talks about relativity and trying to kind of disprove by pure argument one of the uh, pillars of relativity, which is relativity of simultaneity, but completely misunderstands the whole thing, or he doesn't want to understand, possibly.
bomb situation in the train, they can argue the midpoint difference, blah, blah, blah. Okay, fair enough. Touche. Let's take another example, right? So here we have balls A and B, and they're being held by a platform that will drop out from under A and B at the same time.
Now, I could be the person who asks at the same time in which reference frame, and this would be a legitimate question, but for the interest of this argument, I'm not going to do it, and we all know that he wouldn't be able to answer.
When the moving observer and the stationary observer intersect, the stationary observer will see these two balls A and B fall, and they'll hit a balance beam at points A1 and points B1 at the same time. Now, what will happen when these balls hit the ground or hit the balance beam? They're going to hit the balance beam at the same time, and it's not going to cause any tilting or deviation in the balance beam, and they're going to bounce back up a little bit and then go off to the side or whatever. Not important what they do after they hit the balance beam, but they're going to hit this at the same time, and they're both going to equally bounce back. Now, in the moving frame, relativity would say that the B ball would hit first, which would cause a deviation in the landing. So what they would be putting forward,
it would not. Now, I thought about this for a fair while, I will admit, until I realized that the signal that such an event happened in the balance beam can at the fastest only travel at the speed of light. So, I will show this very later on, but in the moving reference frame, the ball B would indeed hit the balance beam first, but just as the signal that that ball B has hit the balance beam would hit the position where ball A hits, ball A would actually hit. because at the fastest it travels at the speed of light, so at the very, very latest they would reach this position at the same time for the moving observer, thus causing the same result as for the stationary observer.
Word.
Just in a different perceived time, in my opinion.
That this would happen. Second. So these get released at the same time, and that they're at the same level. I just moved it to be simple for the motion down. So here they're coming down. They're coming down. Now they're going to say that B1 hits first, and it's going to cause a deviation, and then the balls are going to go, in different directions because of that. But in reality, when these balls hit,
again, in reality has no meaning in relativity.
They're going to bounce back up for the stationary observer and for the...
They will do the same for the moving observer because you don't understand relativity.
moving observer, regardless of the perceived B hitting first, right? Now, how could the stationary observer, or how could the moving observer ever confirm this? Well, as he's moving away, he can look back and see the result of the balls bouncing up together at the same time. And we also have the stationary observer here who confirms the simultaneous event. So
it's not important what the stationary observer confirms because he only can confirm things in his reference frame.
In reality, regardless of velocity, all events occur simultaneously.
When you try to talk about relativity and you throw out one of the core components of relativity, it doesn't really throw a good light on you now, does it, Alan?
And this is further backed up by GPS.
Yeah. Now, he goes on now to talk about GPS, which is a separate issue that I would like to address at a separate occasion, if I can find the time. But for now, let's actually go and talk about the balance beam thingy. All right, so here we are, not back at the OneNote notebook. We are back at the RNote notebook because it works better on Linux. Okay, relativity of simultaneity. I recommend you watch the other video first. First of all, before we start into anything, there is no preferred reference frame. You can only talk, and I'm only talking, of course, about special relativity, and that's simplified because length contraction would apply. And even though it wouldn't be, it wouldn't change the overall argument, it would still change some of the things and the way that I explain them. But the overall result would be the same. So when Alan says in reality, which reality? I talked about this in the video. Two observers in different reference frame can see two different things and both can be right. This is the thing about simultaneity, relativity of simultaneity. And this is at the very core of special relativity, are the effects of relativity. And there is no single reality. Now that we have done that, he says that the two reference frames are not related to one another. I disagree. You can transform from one frame to the other using the Lorentz transformation. I've listed the formula down here for if we move in x direction, not particularly important. The takeaway message here is neither frame is real or unreal, more so than any other frame. Now let's talk about the example. The example, and I will be completely honest here, was a little bit tricky. Okay, I had to think about it for some time before I came up with a solution, and I'm still not 100% sure this is the correct solution. I will probably ask a colleague and friend of mine who does a lot with relativity. She probably can answer this question for me more swiftly so than I can. So, for observer D, which is the one that is moving at a significant fraction of the speed of light, first of all, he sees B occur. Right, let's call him Daniel. Daniel rides along the train alongside the balance beam, and of course, first of all, he sees B occur because of relativity of simultaneity. Now, I've drawn the balance beam here to be bendable. It doesn't, of course, need to be. I just want to signalize that the material responds to B. Right. So the balance can at the fastest move at the speed of light. So B occurs, it pushes the balance beam down on one side. The other side doesn't go up because the signal hasn't reached the other side yet, of course. So the bend, I call this the bend within the confines of this example. You don't necessarily need to call it a bend. You could say the material response or some kind of change within the arranged atoms of the balance beam, things like that. So the band moves at the speed of light towards the left, so towards A, right? And the band continues to move, and at the best, it reaches the point A just as A hits the scale itself. So what you would see from that is that, well, the two balls would hit the balance beam at separate times, and yet the balance would not be particularly out of balance in that one end goes down as the other rises up. I drew it here that this end goes down. By that I just mean that this balance beam has already reacted to this change. I stopped the bend at the other half because if it was a real bend, it wouldn't extend, of course, until the end. This is maybe not an ideal depiction here, but the thing that I would like to make clear is the response of the beam travels through the beam until it reaches the point at which it hits, which is, at the worst case, precisely the time where ball A hits. So the balance beam would, in fact, stay balanced, just that ball B would be the first one to hit the balance beam, and just as ball B would get the force to leave the balance beam, ball A would hit, and ball A would still fly upwards, even though ball B has already left, because there is still tension left in the balance beam, because it hasn't had time yet to react, because it can only react at the speed of light at the very best. So this is what I think would happen. I maybe haven't drawn it in an ideal case here, but this is what I think would happen. So no rules are broken, no laws of physics were violated. Both balls will bounce straight up, just in a different order. This is what I think would happen, which differs quite a lot from Alan's prediction, because he did not factor in the fact that the information that the two balls have hit can only travel at the very, very best at the speed of light within a medium, but typically they would move at the speed of sound in a metal. For if we say the balance beam is metal, which is only like a couple of times faster than the speed of sound, so like 20 or 30 times the speed of sound, or even give it 200 times the speed of sound, doesn't matter. It's still a lot slower, right? So he forgot to factor it in. Of course, if you drop one of the core tenets of special relativity, and that is that things can, at the very best, only move at the speed of light, well, obviously you're going to get a nonsensical prediction. So Alan's prediction is wrong. He applied the good old flat earth technique of not understanding our position and then just arguing against their made-up position that isn't really our position. So he pulled a straw man unknowingly. Yeah, so the verdict remains: flat earthers don't get relativity, and that's, I think, an absolute statement. And with that, I will leave you to it. If you have another suggestion as to what would happen, please feel free to leave it in the comment section. Should I be critically wrong, and my colleague tells me so, I will make a follow-up video, but I hope I won't. Yeah, so with that, I will leave you, and I will see you in the next video. If you enjoyed this video, maybe consider leaving a like. If you enjoyed it a lot, maybe considering subscribing. And I will see you in the next video. Until then, have a good time. Goodbye!